Good morning students, warm welcome to again the next session of your NCERT 360 degree. So today we'll be starting with 12th part, and the very first topic we'll be covering today, that is basically from the first two chapters of your NCERT part 1, 2025 and 2026 edition. So this is NCERT part and the chapters are electric field and charges and electrostatic potential and capacitance. So let's begin the NCERT part, and I welcome you all again for this session. So this is regarding electric charges and fields, and the second chapter would be electrostatic potential and capacitance. So very first question we have, that is, consider three charges Q1, Q2, Q3 each equal to Q at the vertices of an equilateral triangle of side L. What is the force on a charge Q with the same sign as Q placed at the centroid of the triangle as shown in figure? So this question is particularly from the superposition principle. So we know Coulomb's law, we know Coulomb's force. Coulomb force is a vector force. So we have to find out the net force. So let's draw this configuration again. So you have this configuration. So this is charge Q, this is Q, and this is Q. And this is equilateral triangle of side L. So we have one charge capital Q, and that is at the centroid. So what are the forces experienced because of all these? So this is charge 1. So let's suppose this is force 1. This is charge 2. So this is F2. This is charge 3. So this is the force F3. Now if you look at these forces individually, so can you see force F1, F2 and F3, all forces are of equal magnitude, and this is equal to K Q1 Q2, so that becomes Q square. So but this is capital Q, one of the charge is capital Q. So this is the one, and by this distance, which is, I may call it as, this is basically L by root 3. So this is, let's suppose we call this distance as R only primarily. So this is R square. Now what's next? Now if you look at F3 and F2, they are at 120 degree. So let's find out the resultant of these two forces first, and let's call this as F4. So if I ask you to find out F4, so let it be here only. So F4 is basically F2 square plus F3 square plus 2 F2 F3 and cos of 120. So this is cos of 120, and this is the whole under the root, because just to minimize the mathematical calculation part, we can simply put it as F. So this is F square, 2F square and cos 120. Do we have an idea about what cos 120 is? So this is minus 1 by 2, and when you find out the resultant, so that comes out to be 4 only. Oh sorry, that comes out to be F only. So any doubt from this part? So very good morning. Most of you have joined. Very good morning. So, shall we move? F4 is mathematically, numerically equal to F only. Now, if you look at F4 and F1, so F4 and F1, they are equal and opposite. The magnitude of F1 is also F. So, what is the net force experienced by this charge Q at the centroid? So, that is resultant of F4 and F1. So, F1 and F4 are exactly equal and opposite. So, the net force experienced by capital Q would be the resultant of these two, and that is 0. So, this is the very fine example of your superposition principle. Any doubt from this part? Any doubt? So, shall we move? So, I would like to add, whenever you have a symmetrical configuration, so because this is a symmetrical configuration where all the three charges are equal and they are symmetrically placed, and at this point of symmetry, that is centroid. So, for this situation, the net force will be equal to 0. If you extend this concept to a square configuration, let's suppose this is Q, this is Q, this is Q, this is Q, and this is again a square configuration. And if I ask you what is the net force experienced by capital Q placed at the center, that is, so we have to find out the net force on capital Q. So, again going by the same concept, because this is again a symmetrical configuration. So, the net force on capital Q would again be 0. So, this is the concept of symmetrical distribution. Any doubt? So, very good morning Sanjana, Yuvraj, very good morning. And there are other students also. Shall we move? So, student name Akhand. I mean, like, I would rather suggest you, bacha, ki you better focus on the content and just come out of all this, whatever you are asking. So, you should not worry about any of this. So, shall we move? Let's move to the next question. Now, consider the charges Q, small q again, and minus q placed at the vertices of an equilateral triangle as shown in the figure. What is the force on each charge? So, we have to find out force on each charge. So, this is minus q, this is plus q, and this is also plus q. So, they are labeled as charge number 3, charge number 2, and charge number 1. So, shall we find out the force on each charge? So, let's find out force on each charge. Now, first we'll find out force on this charge minus q. We know minus q is being attracted towards charge q because that is positive one, and also the force experienced by minus q due to charge q1, that is also there. So, we have labeled these, rather the diagram itself has suggested you, the forces are labeled as F32, the force experienced by charge 3 due to charge 2. Similarly, F31, the force experienced by charge 3 due to charge 1. this is an equilateral triangle, so this angle is 60 degree. So as you can see, the charges, they have the same pairs. So F32 numerically is equal to F31, and this is simply labeled as F. So resultant of these two forces would definitely be like this. So what is this? So they are labeling it as F3. So F3 is F31 square plus F32 square plus 2 times F31 F32 and cos of 60 degree. So when you put the values, substitute the values, so this is F, this is also F in terms of magnitude. So we have 2F square, cos 60 is 1 by 2, and when you solve it, it becomes root 3 times F, and this root 3 times F. So F is basically the force between this combination, this pair, so that is K Q square by this separation L square. So this is the first resultant force experienced by charge placed at C due to the other two charges. Any doubt from this part? Yes, Yuvraj, any doubt? So I think we should move on. Now let's find out force on Q1. So Q1 being positively charged, so it experiences force due to charge at C. So the direction of force is this one, and this Q1 being positive will be repelled by the charge at B. So this is another force. So magnitude wise, again these two forces are of same magnitude because we have the same magnitude pair. So the resultant of these two will be somewhere here, and they have labeled it as F1. So again F1 being the resultant of these forces, F13 and F12. So this is also F square plus 2F square. Now because this is an equilateral triangle, this angle is 60, so this angle is 120. Cos 120 is minus 1 by 2, and when you solve it, it comes out to be F only. So any doubt? Any question from this part? Yes, Yuvraj. Yes, Sanjana. You would like to ask anything? Sure. So shall we move? Now similarly, going by the same fashion, if you just look at the force experienced by charge Q2 due to charge Q3, so this is again F23, and we'll just simply label it as F only in terms of magnitude. And this force experienced by charge 2 due to 1, this is also F. So they are also inclined to each other at an angle of 120. So going by the same fashion, the resultant force would come out to be F only. So very good, Yuvraj. Any doubt? Anything you would like to ask? And F we know, this is K Q square by L square only. So this is the concept. So it clearly revolves around your superposition principle, and for this you have to have strong vector algebra. So if you understand the vector concept, how to find out the resultant of two vectors or maybe for any number of vectors, then these questions are of very easy nature. So I think we should move on. Still If you have any doubt, you can confirm. Good, Sanjana. Now, the next question that involves your concept of electric field. So, like Coulomb's force between two charges is a vector form, is a vector quantity. Rather, electric field is also a vector quantity. So, 2 point charges Q1 and Q2 are of magnitude 10 to the power minus 8 Coulomb, that is plus, and the other charge Q2 is minus 10 into 10 to the power minus 8 coulombs respectively, are placed 0.1 meter apart. So, this is Q1, this is Q2, and they are separated by 0.1 meter. Calculate the electric fields at points A, B and C shown in figure 1.11. So, now this time we have to find out electric field. So, how you go with the electric field concept? Electric field is again a vector quantity, and just to make your concept easier, we know electric field due to point charge, positive point charge at any point will be radially outward, and if electric field is due to a negative charge, that would be radially inward towards the negative charge. So, applying that principle only, so we have to find out electric field at points A, B and C. Fine. So, this is point A. Got it? So, we have to find out electric field at point A. Now, if you look at the figure, this configuration involves two charges. One is positive nature and the other charge is of negative nature. So, electric field at point A due to charge Q1. So, this is radially outward. So, this is E1, and at the same point due to negative charge Q2. So, that would be towards the negative charge radially inward, and this is E2. Got it? So, this is the simplest concept. So, electric field at A, and when you add these two vectors pointing in the same direction, so resultant would be this way only. So, once we are clear about the direction concept, let's work out with the magnitude. So, that would be E1 plus E2. Got it? So, otherwise in vector form, in superposition principle form, so we simply put it in the vector form, but we are clear about the direction. So, let's work out the magnitude part. What is E1? So, electric field due to point charge is KQ by R square. So, this is K. Q means 10 to the power positive charge. So, I will simply put it simply in numerical form first, by R square. Can you see this R? So, this is 0.05 R square plus KQ by R square, and this is the concept for magnitude. So, value of K, as we all are aware of it, and what is Q? 10 to the power minus 8. So, when you add it, it becomes twice of this, and this is 0.05 whole square. So, please try to work it out what you will end up with. I am giving you a minute to attempt this and give me the answer. I am waiting for this calculation part to be done by you people. Yes, you have to simply do the multiplication part, and the rest of the calculations you can have it. So when you solve it, it comes out to be 7.2 into 10 to the power 4, because this is the electric field. What are the units for the electric field, SI units? It's force per unit charge. So shall I call it as Newton per Coulomb? So this is the electric field, resultant electric field towards right hand side, and this is the magnitude for that electric field. Any doubt from this part? Any doubt? Fine. Now we have to work out electric field. So we are done with electric field at point A. Now we have to find out electric field at point B. Going by the same fashion, going by the same process, at this point we have electric field due to two charges. One is positive charge, so electric field at this point B due to positive Q1 would be radially outward. So this is E1. Got it? And electric field at point B due to negative charge -2, that is towards the charge. So this is E2. Got it? So what is the net electric field in terms of magnitude? So this E1 is KQ by R square, and E2. If you look at the separation, this distance is 0.05 and this distance is, so this is 0.1 plus 0.05. So this separation is more. So E1 would definitely be more than E2. So the resultant would be E1 minus E2. So what is this E2 is? KQ by 0.15 whole square. All these units are already given to you in standard SI units. So otherwise we have to be very particular about the unit conversion part. And so this is 9 into 10 to the power 9. Q is 10 to the power minus 8, and this is 0.05 whole square minus 0.15 whole square. So just give me the answer for this calculation part also, what you will end up with, please. If you keep doing all these calculations, that would help you to be more confident, and precisely you will gain the strength in your mathematical part, and that would give you more confidence. So this number comes out to be 3.2 into 10 to the power 4, and unit wise is again Newton per Coulomb. So this is electric field at point B due to this configuration, Q1 and Q2. Now we have to find out electric field at point C now. So let me just work out with some different shades so that you can differentiate it. Now when you look at point C, electric field due to positive Q1 would be radially outward. Got it? Electric field due to negative Q2 would be radially inward, and this is E2. You got it or not? Fine. Now this separation, this charge in terms of magnitude, these charges are same. This separation, this R 0.1 meter is same for both. So E1 and E2 are numerically same, that we have observed it in this situation also. But that E1 and E2 are different for this because of the difference in the separation. So now if you split this E1, what this angle would be? Can you give me this angle? What this angle is? We can find out this angle. So this is 60 degree, pi by 3. So that would be resolution of E1 along this one. So E1 cos 60, and this is E1 sin 60. I think this resolution part is clear to all of you. Are you clear about this concept? Is this visible clearly, or shall I make use of some different color if you are okay with this? Now similarly, if you split E2, so this angle is again 60 degrees. So this is E2 cos 60, and this is E2 sin 60. We have already stated E1 and E2 are equal in magnitude. So this E1 sin and E2 sin, they'll mutually cancel out each other because they are in opposite directions, so they'll mutually cancel out each other. So the resultant electric field would be because of these two, and the direction of the resultant electric field at point C would be this one. So this is EC, and this is E1 cos 60 plus E2 cos 60, and E1 and E2 are equal. So this is 2E1 cos 60 degree. So this is 2 times E1. E1 is K Q by R square. So this is 0.1. So this is and finally the calculation part. When you do this calculation, you will end up with the net resultant electric field at point C. This is, I'm waiting for the calculation. Please go ahead, giving you half a minute to 1 minute. Please complete your calculation. So this comes out to be 9 into 10 raised to power 3 unit wise Newton per Coulomb only. So this is the same concept, and one of the beautiful examples we have in this chapter. Reason being, this example has given you the approach to solve for varieties of situations for a given pair of charges. And if you have understood this topic, if you have understood this, the way we have approached this numerical, I think you can solve varieties of numericals based on superposition principle for the electric field. Any doubt now you have? Any doubt? So Yuvraj, Sanjana and Rajvi all are doing okay. Shall we move? Okay, fine. I'm moving to the next topic. Now, this is again one of the important, and I would rather say this numerical, which is an example from your NCERT part. This example is quite important because this example, this variety of question has been asked in your CBSE board as well as your NEET part number of times. So this is again very important. It says the electric field components in figure 1.24 are Ex alpha x power 1 by 2, Ey and Ez are 0, in which alpha is also known to us as a constant with dimensions, with units. Calculate the flux through the cube and the charge within the cube. Fine. So this question has two parts. One is the flux part. So let me brief. Flux is given by E dot A, and this is EA cos theta, where E is electric field vector, which is given to you along x-axis. So can you see the electric field along x-axis? And A is the area vector, and theta is the angle between electric field vector and area vector. Now this cube, this configuration, so we have to find out through this closed surface, which is a cubical concept. So this cube has 6 surfaces. So when you are asked to find out the flux through all the surfaces independently, then you have to find out flux through each of the face independently. So let me just help you to understand this concept. So let's suppose if I label this as the surface 1, this part. Now electric field is along x-axis and its area vector is this one. So area vector is this one. So what is the angle between electric field vector and area vector? So as you can see it, this is 90 degree. So the flux through the first phase, that is on the top, that is the flat surface on the top, or the top surface of this cube configuration. So the flux through this first part would be 0, because cos 90 is 0. So the flux through the first part is 0. If you look at this one, I label this part as 2, and this is the area vector, this is the electric field vector. So flux through surface 2 would also be 0. If you look at this front part, so if I label this front part as 3, so if you look at the front part of your cube, so its area vector is radially outward and electric field is still along the x-axis. So for this part also flux is 0, because area vector is again normal to the electric field. And the surface which is just at the back of it, its area vector is radially outward in the plane. So for the fourth part, flux would still be 0. So this is the beauty of this. So out of 6 surfaces for this cubical configuration, the contribution due to 4 surfaces which are normal to the electric field direction, so they are contributing no flux for the configuration. Now we are left with only 2 parts. What these 2 parts are? So can I label this part as 5th and this surface as 6th? So for this part, area vector is radially outward, and look at this electric field. So if I label this electric field as E, so this is along x-axis given to you as alpha times x power 1 by 2. So this is alpha times. Now what is this axis? If you look at the configuration, so this is A and this is another A. So here we have 2A power 1 by 2. So this is electric field and this is the area vector. So flux through this part, if I label this as flux 5 through this part, so that is electric field, that is into area, and area of this part is A square, and this is, so area vector is along electric field vector. So for this theta, that angle is 0 degree. So this is cos 0 degree, and cos 0 degree is 1. So do we have understood how we are getting flux 5, flux through this phase, which we have labeled it as 5 number. Now for this part, electric field is still along x-axis, but its area vector is like this. So this is inclined at 180 degree. So what is the flux through surface 6? So this is alpha, and this is at separation A. So this x part is A only. So this is A power 1 by 2 into area, that area of this part would still be A square. So for this part, area would again be A square, but this time cos 180 is minus 1, and the net flux, flux being a scalar quantity, would be sum of all the flux from surface 1, 2, 3, 4, 5 and 6. But we have already proved the flux through the 4 surfaces is 0. So the net flux would be flux through surface 5 minus flux through surface 6. Do we understand? And you simply put the values. So this A is 0.1 square, this is 2 times and you have to simply do the mathematical part, calculation part, and that would give you 1.05 numerically. This is the flux net. And what units you have? Can you give me the units? So for electric field, Newton per Coulomb into area, that is meter square. So this is the net flux through this cubical configuration when it is placed in electric field. Any doubt from this part? Any doubt? Surely? Shall we move? Shall I give you just a bit of twist in this numerical, so that would add on more to your concept. Let's suppose, assume electric field to be just alpha, which is like constant. Then what is the net flux through this cube? If I give you electric field is constant, that is still directed along x-axis only, but numerically it is constant. So let it be Ex. Ex means this electric field is along x-axis only, but this time it is of constant magnitude. Then what would be the net flux through the same cube? will go by the same fashion, will follow the same process. So just look at this. So phi 1, phi 2, phi 3, phi 4 would still be 0, going by the same fashion, because their area vectors would be normal to the electric field vector. But phi through the surface phi, flux through the surface 5 and flux through the surface 6. So electric field being constant, so flux through 5 and flux through 6 would be numerically same and they would be opposite. So this would be EA cos 0, but this would be minus EA. So what you will observe, magnitude wise same, but they have the opposite sign because cos 180 is there. So if I just put it like this, flux through 5 and 6 would be like this. So the net flux for this configuration would come out to be 0. So had your electric field being a constant quantity, then flux would have been 0 through this cube. So this is a slight alteration in the same situation. So this was all about the flux through the cube. That was your part A. Now let's move to part B. Part B says charge within the cube. Now once we are supposed to find out the charge, then as per your Gauss's law, so this shade is clearly visible to you, or shall I make use of some other color? I think red would also work really well on this white background, so I should make use of this red also. So as per Gauss's law, E dot dA for the closed surface is equal to charge enclosed by epsilon naught. And this flux for the first configuration, for the original question I am talking about, where this electric field is known to us as alpha x power 1 by 2. So the net flux was 1.05. So 1.05, and if you multiply this with the epsilon naught, which is 8.85 into 10 to the power minus 12, and that would give me the charge enclosed in this. Can you work it out? So this is close to 9.27 into 10 to the power minus 12. So this is the charge, and definitely SI unit for the charge would be coulombs. So that is the amount of charge enclosed by this cube in the original statement, in the original configuration, in the original question we have. Any doubt from this part? Surely well. Any doubt? So I think we should move on. Now, from the back exercise questions, what is the force between two small charged spheres having charges of this 2 into 10 to the power minus 7 coulomb and 3 into 10 to the power minus 7 coulomb placed 30 centimeter apart in air? This is a simple question. So you have two charges, Q1 and Q2. If they are separated by distance r, then force when they are placed in air, air is also considered to be as medium, but we are considering air to be close to your free space. So that force is given to you as K times Q1 Q2 by r square. So put the value of Q1 and Q2. So this Q1 is what? 2 into 10 to the power minus 7, and this is 3 into 10 to the power minus 7, and 30 centimeter means 0.3 meters whole square. And just give me the calculation part so that, so this is the answer for this. Just do and multiply, go ahead. So this is 6 into 10 to the power minus 3 newtons. Any doubt from this part? Surely well. So Subrat, very good. Now we have next question. 4-point charges QA, QB, QC and QD all are located at the corners of a square ABCD of side 10 centimeter. What is the force on a charge of 1 microcoulomb placed at the center of the square? Fine. So we have a square configuration. So we have A, B, C and D. Charges 2 microcoulomb minus 5 microcoulomb plus 2 microcoulomb minus 5 microcoulomb. So square of side 10 centimeter. Got it? What is the force on a charge of 1 microcoulomb placed at the center of the square? So this is 1 microcoulomb. So this is again based on the superposition principle we have. So will you make an attempt or shall I help you? Fine. Now first, is this a symmetrical configuration? Is this a pure symmetrical configuration? Answer is no, because the charges are different. Then how you will find out the net force? This seems to be a symmetrical configuration because there is a square. Got it? So first, the force experienced by this 1 microcoulomb due to charge at A. So this would be radially outward. Let's call this force as F1. Got it? Now, what is the force experienced by charge 1 microcoulomb due to C? This is radially outward and this is also F because the pairwise, so this is 1, this is 2 and the separation is same even for the other one. These two forces are equal and opposite, will mutually cancel out each other. Do we understand? Any doubt? Yes? Any doubt? Now, for the other two charges, look at the force experienced by 1 microcoulomb due to charge B. So that would be towards, and let's label this force as F prime. Force experienced by 1 microcoulomb due to minus 5, that is placed on D, that is also equal to F prime. So these two forces are also equal and opposite to each other. So the net force experienced by 1 microcoulomb placed at the center of the circle would come out to be 0. Any doubt? Any doubt from this part? This is, we have not just touched the formula, we have just discussed it conceptually, and because this seems to be a very approachable conceptual question, so this is how we have approached it, and the net force would still be 0. Any doubt? Any doubt you have? I think then we should move on. Now we have next question. Next question is also interesting one. It says 2-point charges QA and QB are located 20 centimeter apart in vacuum. What is the electric field at the midpoint O of the line joining the two charges? So we have, this is QA and this is QB. So this is 3 microcoulomb, this is minus 3 microcoulomb. They are separated 20 centimeter. This is more or less like a dipole. This is like a dipole. What is the electric field at the midpoint O? So this is the midpoint. So as we have attempted earlier also, electric field at this midpoint, at this, let's call this midpoint as P. So electric field due to charge A would be radially outward, and electric field due to, at the same point P, electric field due to charge B would be radially inward. So both the electric fields are in the same direction. Do we understand? So the resultant electric field would be like this, and this resultant electric field would be electric field due to A and electric field due to B. So that means K Q by, now what is this? This separation is 10 centimeter and 10 centimeter is 0.1 square, and EB is also mathematically same. So we'll simply put it as multiply by 2. Can you give me the answer for this? So put the value of K as 9 into 10 to the power 9, and this is 3 into 10 to the power minus 6 and B is, so multiply by 2 by 0.1 square, and that would precisely give me the answer for this. So that gives me electric field, so this is Newton per Coulomb. Now, if a negative test charge of magnitude is placed at this point, what is the force? Now you place test charge minus Q, and the electric field is in this direction. So we know force per unit test charge is electric field. So the magnitude of force would be Q times E. So what is this negative charge is? So this is 1.5 into 10 to the power minus 9 multiply by 13.5 multiply by 10 to the power 5. Now this is quite interesting. What is the direction of the force? Because this is a negative charge, so the direction of force would be opposite to this. Got it or not? And this is numerically equal to, can you multiply these two factors? So this is 20.25 into 10 to the power minus 4 newtons. So this is for this configuration. Any doubt? Now if I add on one more concept, if I ask you potential, electric potential at point P, this is to be covered in the next chapter, but because this is a part of your today's class, so electric potential is due to charge A plus due to charge B. So electric potential at point P due to charge A is positive, whereas for the negative charge numerically you have the same value separated by the same distance. So that is minus V. So the net electric potential at point P would come out to be 0. So any doubt from this part? An electric dipole with dipole moment is aligned at 30 degree with the direction of uniform electric field of magnitude. Calculate the magnitude of torque acting on the dipole. We know whenever we have any electric dipole placed in uniform electric field, the net force experienced by the dipole in uniform electric field. So this is your uniform electric field and this is the dipole at an angle theta. So the net force on this dipole in uniform electric field would be 0, but it experiences torque and that torque is given by Pe sin theta. So dipole moment 4 into 10 to the power minus 9, electric field 5 into 10 to the power minus plus 4 rather, and sine of 30 degree is 1 by 2. Can you give me the value of the torque experience? So this is the numerical value of the torque. Any doubt from this part? Shall we? Now we have very interesting situation. A point charge plus 10 microcoulomb is at a distance 5 centimeter directly above the center of a square of side 10 centimeter as shown in figure. What is the magnitude of the electric flux through the square? Okay. Now consider this is your surface, flat surface. This is a square plate. A charge is placed 5 centimeter above this surface. Can you see this? Now the best way to approach it, just complete this square. You just raise all the edges and you just complete this square. So let's suppose this is a square and a charge is placed over here. I'm just suggesting you just raise all these vertical bars. What you will have, this will give you a square configuration, and once the charge is enclosed in that surface, you can easily apply Gauss's law. So this imaginary surface which has enclosed the charge completely, so we call it as a Gaussian surface. Now we can apply Gauss's law, which clearly says the total flux through this closed surface is charge enclosed by epsilon naught, and this is for the complete cube. But we have to find out flux through this square part only. So square is just one of the surfaces out of the 6 surfaces of a cube. So we have flux through the square part would be given by this expression, and charge is known to us as 10 into 10 to the power minus 6. So this is 1/6 and this is 8.85 into 10 to the power. So that flux numerically, when you calculate this flux, so this would be 1.8 something, precisely 1.88 into 10 to the power plus 5 or minus 5. So when you look at this, it comes out to be plus 5, and this is a flux. So unit of flux we all know. What do you mean by flux? So that is Newton per Coulomb into meter square. Any doubt from this part? and this is one of the easiest approach we have for this numerical. Shall we move? Now the next question is again basis on the electric flux. A point charge causes an electric flux of minus 1 into 10 to the power 3 Newton meter square per Coulomb to pass through a spherical Gaussian surface of 10 centimeter radius centered on the charge. If the radius of the Gaussian surface were doubled, how much flux would pass through the surface? Now, so there is some charge and you have flux. The total flux, which is given to you as E dot dA for the closed surface, that is equal to charge enclosed by epsilon naught. And this law has clearly stated, has clearly given to you that this flux through this closed surface would be independent of its shape and size. So had it been irregular closed surface, then flux would have been same. Had it been a size double the size of the original one, so here we are just making the size doubled, will make no difference. So independent of size, so if you make the size double, the flux would still be same because this is independent of the size. And the second part is, what is the value of the point charge? So flux is given to you as 10 to the power 3 multiplied by 8.85 into 10 to the power minus 12, and this is the amount of charge enclosed. Any doubt from this part? Shall we move? Now, a conducting sphere of radius 10 centimeter has an unknown charge if the electric field 20 centimeter from the center of the sphere is this and points radially inward. What is the net charge? So it's radially inward. So what do you mean by radially inward? So if it is radially inward, we know this charge has to be a negative charge. Do we understand it or not? So electric field due to point charge is given by this formula kq by r square. So electric field is known to us as 1.5 into 10 to the power 3. Value of k is 9 into 10 to the power 9. Q we have to find it out, and its radius is, what is this radius is? But radius has no significance because we are given this distance as 20 centimeter. So this is 0.2 meters, and that is how you calculate the charge. Can you give me the value of charge for a minute? .6 into 10 to the power minus 9 Coulomb. Shall we? An infinite line charge produces a field at a distance of 2 centimeter. Calculate the linear charge density. So this is one of the applications of your Gauss's law. So you have infinite line charge, got it? And if electric field at this point, we are supposed to find it out. What is the process? We'll simply complete this, we'll enclose it with a Gaussian surface, imaginary Gaussian surface, and this has a linear charge density lambda, which is a linear charge density. So when you use your Gauss's law and when you find out electric field at this point, which is at a distance r, so what is the value of electric field? So electric field is lambda by 2 pi epsilon naught r. Got it or not? and you simply just multiply so when you put all the values together, you will end up with lambda, and this lambda, can you find out the lambda? Electric field is given to you, so this is given to you 2 pi epsilon naught. Make use of this, 1 by 4 pi epsilon naught is equal to 9 into 10 to the power 9. So you can simply multiply it with 2, divided by 2, then make use of that concept. Put the values. R is also given to you as 2 centimeter. So when you solve it, this lambda is 0.1 microcoulomb per meter. So this is the standard microcoulomb per meter. So that becomes the linear charge density. Any doubt? A uniformly charged conducting sphere of 2.4 diameter has a surface charge density of this much, 80 microcoulomb per meter square. Find the charge on the sphere. So this is the next question, we have to find it out. So this is a sphere of radius r. You got it or not? So surface charge density. Surface charge density. So that is, let's suppose surface charge density is sigma. And that is charge per unit surface area of this spherical configuration. So this is known to us as 80 microcoulomb per meter square. When you multiply it with the 4 pi r square, so radius is 1.2, and you will end up with the value of q. So this q comes out to be 1.44 into 10 to the power minus 3 coulombs. So this is the value of the charge we have. Then what is electric flux? Q by epsilon naught. So value of Q is there. Epsilon naught is we know, and that would give you the answer for the flux. Any doubt from this part? Shall we move? Now we have chapter 2, calculate the potential at a point P due to a charge 4 into 10 to the power minus 7 coulomb located 9 centimeter away. So we know potential due to point charge is given by kq by r. So value of k is this much, q 4 into 10 to the power minus 7 by r 9 centimeter away, so 9 into 10 to the power minus 2, and that would give you the answer for the potential, and that means, so this is simply 4 into, so this 9 goes with this goes minus 5, so this is 4, unit wise this is volts. Obtain the work done in bringing a charge from infinity to the point P. We know by definition work done per unit test charge is electric from infinity to point P is potential at point P. So work done is simply charge into potential. So what charge you are bringing from infinity? 2 into 10 to the power minus 9, potential is 4 into 10 to the power 4, so that makes it 8 into 10 to the power minus 5, and because we are doing it as work done, so that would be in joules. Any doubt from this part? Now we have 2 point charges. So 2 charges, 3 into 10 raised power minus 8 Coulomb and minus 2 into 10 raised power minus 8 Coulomb are located 15 centimeter apart. So this is 3 into 10 raised power minus 8 and this is minus 2 into 10 raised power minus 8 are located 15 centimeter. Got it? At what point on the line joining the two charges is the electric potential 0? So this is the line. Got it? So first we'll find out a point somewhere between these two charges, somewhere between these two charges. So let it be point P. If I call this distance as x, so this would be 15 minus x. So potential at P is 0. So it means potential due to negative charge is K minus 2 into 10 to the power minus 8 by x plus potential due to positive charge K 3 into 10 to the power minus 8 by 15 minus x. So it means 2 into 10 to the power minus 8 K times by x is equal to K times 3 into 10 to the power minus 8 by 15 minus x. What do you do? You simply find out the value of x. So this K, this 10 to the power minus 8, it goes on both the side. Can you give me the value of x? So this x comes out to be 6. So this is 6. Now can we have any other point on this center line, on this axial line of these two charges? I think we can find out one more point, and that is outside these two charges. Can you find out a point that is outside these two charges? So let this point again be P, which is at a distance x from one charge, and this distance would be 15 plus x, and going by the same fashion. So this is K Q by x is equal to K 3 into 10 to the power minus 8 by 15 plus x. That would give you another value of x. Got it? And this x comes out to be 30 from one charge, and it means from the 3 into 10 to the power minus charge, that would be 45 centimeter. We'll keep the units intact, centimeters, so that will not make much of the difference. So there would be 2 points. One would be definitely between these two charges, and the second point would be outside this configuration. Any doubt from this part? Any doubt? So I think we should move on to the next question. Now we have 4 charges are arranged at the corners of a square of side ABCD of side D as shown in figure 2.15a. Okay, 2.15. Then the first part, A part, says find the work done required to put together this arrangement. You know, to bring this arrangement in the final configuration, work done is purely depending on the final configuration. How we have obtained this configuration is not important, but what is the final configuration? What is the final? So this is the definition. If you just find out the potential energy of the system, because once the configuration is well established, so you have a potential energy, and the concept of potential energy says work done in making that configuration. So what is the potential energy of this system? You got it? So that would be the answer for this. Work done. So potential energy of the system. We know potential energy for a pair of charges is given by K Q1 Q2 by R. So just look at the pairs. Can you see this is the first pair, this is the second pair, this is the third pair, and this is the fourth pair. So we have 4 pairs which are making 4 corners. So this is 4 times K Q minus Q by R, where this R is the separation D. So these are the 4 pairs which are there. Then apart from that, we have 2 more pairs like this. So this is one pair, K Q square by root 2D, and there is another pair K minus Q that also makes, so this pair minus Q and minus Q also gives you Q square, and this is diagonal root 2D. So just simply rearrange all these will give you the answer for the final one. So this is minus K Q square by D. So this is minus, so because this minus minus makes it plus, so K Q square, so this is 2 by root 2 D. Rather, we can simply cut it as and can write down as minus root 2 also. So that is also one way. So this is the final configuration, and this is the final work done required to settle this configuration. Then the second part, B part, says a charge Q naught is brought to the center of the square. The 4 charges being held at its corner. How much extra work is needed? Okay. Now to define that extra work, again, this configuration is already there. Now to bring more, to bring another charge Q naught, that extra energy required is basically the extra work done. So that is work done per unit test charge gives you potential at the center E. So now first, if we know the potential at point E, we can find out the extra work done. So what is potential at E? So potential at E is due to all the 4 charges. So this is potential due to A, potential due to B, potential due to C, potential due to D. Potential due to A is KQ by, this is D by root 2. So this is minus KQ by D by root 2. This is again plus D KQ by D by root 2, and this is minus KQ by D by root 2. As you can see, the net electric potential is 0 at point E. So work done would definitely be 0. So that extra work done needed is not there. Any doubt from this part? Any doubt? Shall we move? Now we have example that is from the capacitor part. A slab of material of dielectric constant K has the same area as the plates of a parallel plate capacitor, but has a thickness 3 by 4 D, where D is the separation of the plates. How is the capacitance changed when the slab is inserted between the plates? Fine. So we have plates of area A and the separation is D. Original capacitance is A epsilon naught by D, and this is So potential is given by this one. This is the original potential, where E naught is the original electric field, and that is sigma by epsilon naught. So we know this is the original configuration. Got it? Now a dielectric slab is introduced. Area A, but thickness is 3/4 D. So here in this region, the electric field would still be E naught, but in this situation, electric field would be decreases by E naught by K. Got it or not? So the new potential difference would be E naught into, so if this is 3D/4, so what you are left with? D/4 plus E naught by K, and this is 3D/4. Got it or not? So when you solve it, can you see this? So the potential is, what is this? This is the original one. So the new potential difference between the plates is given by this one, and capacitance is, charge remains same, what the original charge you have by potential V naught. And when you solve it, when you put the value of V naught, so it gives you C naught 4K by K plus 3. So this is how the capacitance would change by a factor called 4K by K by 3, K plus 3, when a dielectric slab of dielectric strength K is introduced between the plates of the capacitor. So any doubt from this part? Any doubt? If you have any doubt, please confirm it, then otherwise we are moving ahead. Now we have another 2.9. A network of 4 10 microfarad capacitors is connected to 500 volt supply as shown in figure. Find the equivalent capacitance of the network. Fine. So this is capacitor 1, 2, 3, 4, and this is the supply 500 volts. All capacitors are of 10 microfarad, and this. So we have to find out the equivalent capacitance between these 2 points. So we label it as A times A and D. Now if you look at the circuit, what do you observe? Can you see all three capacitors, all these three capacitors? What do you observe? They are in series. Can you see all the three capacitors are in series? Yes or no? So what is the equivalent capacitance for these three capacitors? So that would be 10/3, and this 10/3 is definitely in parallel with this. So net C equivalent is 10 plus 10/3, so that makes it 40/3 microfarad only. Got it or not? So that is the net capacitance. Then the charge on each. If you look at this, there is some charge flowing through this and there is some charge flowing through this. So if I label this as Q1, this is Q2. So the same charge is when these three are in series. So charge on this capacitor and this capacitor would be same, whereas charge on this would be Q2. Q is equal to CV. So for this capacitor Q2, what is C? 10 micro. What is the potential applied? 500 volts. So that gives you the answer in coulombs, or if you keep 10 to the power minus 6 there, so that would give you the answer in micro coulomb only. Do we understand it or not? Then what is the charge Q1? That would go same in all the three capacitors which are there in the series. So that is 10 by 3 into 10 to the power minus 6 into 500 volts. So that would be the charge in all the three capacitors which are there in series. So any doubt? Any doubt? Here the potential will be equally divided in all the three because they all are same. So that would be 500 by 3 each in all the three capacitors in series, whereas in this capacitor the potential applied would be same as 500 volts only. Any doubt from this part? Now we have another a 900 picofarad capacitor is charged by 100 volt battery. How much electrostatic energy is stored by the capacitor? So we know electrostatic energy stored by the capacitor is half CV square. So that means half into C, 900 pico minus 12 multiply by 100 volt. So square of 100 volt will give you 10 to the power 4 volt, and that would give you the answer in terms of, so this is 4.5 into 10 to the power minus 6 joules. Got it? Now the capacitor is disconnected, fine, from the battery. So when a capacitor is disconnected, charge would remain same, but it is connected to another 900 picofarad capacitor. What is the electrostatic energy stored by the system? Fine. So once this capacitor is disconnected and connected to another capacitor, so what is the energy, final energy stored? Now can you give me the final potential? The final potential, common potential, is C1 V1 C2 V2 by C1 plus C2, and you can have it just by putting the values. So what is C1 V1? So C1 is 900 pico multiplied by V1. So V1 was 100, but in this case this is uncharged, and then C1 plus C2 will give you 1800. Got it or not? And that gives you as 50 volts. Got it or not? And the final energy of the system, let it be U2. So that is half C1 plus C2 into V square. So put the value of C1 as 900, the other C2 is 900, this is 50, and that would give you the final energy as 2.25 into 10 to the power minus 6. So definitely there is a difference in the energy and where that energy has gone. So this is energy loss, and that is U1 minus U2 is your energy loss. So this energy loss is primarily in the form of heat while transferring the charges, and that heat loss is 2.25 into 10 to the power minus 6 joules only. Any doubt from this part? Surely well. So this is all from our side. So I would like to thanks to all of you, and I hope you people have gained good conceptual knowledge as well as numerical knowledge about these two chapters. So I would like to say thanks to you all again. Myself Puneet Kathuria, your physics faculty at Aakash. So I wish you good luck. Thank you. Hope to see you next time. Bye bachcho.